Welcome to our school at BUE, and really hope that you enjoy these days. I mean, knowing about different topics from general relativity up to inflation and quantum theory, standard model, some issues in condensed matter physics. And we really need your also feedback for that, okay? We always do that every year. But anyway, let me start my lecture. So I'm going to give 4 lectures. I was in the beginning, as usual, try to make it very condensed. Usually ask Dr. Amr to have it 3 lectures, but he keep advising me to make it 4 or 5. I mean, because I tend to talk a lot, so he knows that. So
15 minutes more.
So anyway, let me start with what we are going to do in this mini course in GR. So what we are going to do is doing GR in 3 lectures, okay? And in the last lecture, we are going to talk about black holes and its important problem, information loss paradox, and what are the possible ideas of resolving this paradox. So we are going to present briefly GR in just 3 lectures, and maybe the last lecture we are going to talk about Schwarzschild very quickly, and then Schwarzschild black hole, and then Hawking radiation and the information loss paradox very quickly. So my favorite book in GR is M. Hobson, and I advise you, if you need a nice introduction, it's called General Relativity and Introduction for Physicists. Which is not very illuminating title, but actually it is a good book. And I advise you to actually, if you want to know about GR, I mean, in a very nice, intuitive, geometric and physics, or physical way, it is a good book, okay? So first we are going to review some special theory of relativity. I know most of you, of course, or all of you, know about special relativity, but we are going to review just 2 fixed notations and to remind ourselves what are the basic concepts of this theory. So what are the basic assumptions of this theory? Anybody can tell me?
Speed of light is constant.
Just raise your voice.
Speed of light is constant.
Right, the speed of light is constant. Is this the only assumption?
Physical laws are invariant under the general code.
Exactly. Physical laws are invariant under what?
Lorentz transformation.
Lorentz transformation. Okay, which is a transformation from what frames to what frames? Inertial frames. Okay? Because I could have some transformation which we are going to talk about in GR, which transform you from any frame to another general frame. Okay? So these are the 2 assumptions, as you already said, and one can use these 2 assumptions to drive all what we know about special relativity. Okay? Time dilation, length contraction, E equals mc squared, everything relative. The whole relativistic dynamics, we can drive them from that. But let me just talk about the simple setting in which we have 2 frames, sigma and sigma prime. Sigma prime is moving with some velocity in the z direction, okay? And I want to actually write the space-time coordinates in sigma prime frame in terms of the sigma frame. That's to say Lorentz transformation. So I know that T prime is gamma T minus beta Z, and X prime is X, and Y prime is Y, and Z prime is gamma Z minus beta T. Okay? Here I am taking C to be 1. Okay? This is what we know as Lorentz transformation, provided that, of course, that gamma is 1 over square root of 1 minus beta square, and beta is just V or V over C. Okay? Now, let me put this into a matrix form. If we do that, we'll have T prime, X prime, Y prime, Z prime, and we have a matrix here, and T, X, Y, Z. Okay, this matrix is going to be gamma 0, 0, minus beta gamma 0, 1, 0, 0, 0, 0, 1, 0, and minus beta gamma 0, 0, gamma. Okay? Why I'm putting it in this way? Because I want to write it as a matrix equation. X prime is equal to gamma, this 4 by 4 matrix, times X. Okay? Why it's important to put it in this way? Because this is the idea through which I'm going to generalize the idea of a vector, 4 vector, from 3 dimensions to 4 dimensions. How comes? If somebody asked you, if I have a vector in 3 dimensions, let me call this vector like X. Okay? What is the main property of this vector? Which, of course, we know a vector, it means that we have 3 components, X, Y, and Z component, but this by itself does not really define for me what a vector is. The vector is defined through certain transformations. And this transformation basically in 3 dimension, Euclidean 3 dimension, is just rotation. Okay? So if I have a vector like this, okay, let me call it A, okay, and I do a rotation for this vector and take it to another vector A prime. The question is, what is the relation between A prime and A? This what defines for me what a vector is, not anything else, not the component, nothing. Okay, so A prime is related to a rotation matrix. Let me call it R. Okay, and let me call this the matrix of A. Okay, so A here is AX, AY, AZ, prime, of course. Okay, so this is a column matrix R times A. If I have a vector which transforms in this way, then I can, or if I have 3 components which transform in this way, then I have a vector. Okay? So the same thing here in 4 dimensions. This is a rotation in 3 dimensions which define for me a vector. Why this define for me a vector? Because if a vector as a geometric entity has a very important property. If you transform it or rotate it, it does not change its length. This process does not change its length, which means that A prime transpose, okay? This is how I get the norm. right? If this is a vector A transpose is going to be the row vector. So if I multiply a column with a row, I get a number, which is the length. Okay? And now I'm going to do the same thing with the right hand side. So I have R. Okay? So I should take this A, okay, multiply it with its transpose, okay? And in this way, you will find that it is R, okay, R transpose. Let me do it in full details, okay? I have A here, which is R A, okay? Or I should make it the reverse, I think. No, this is right, okay? So RA with A, so it's supposed to give you something like that. So it's A, R transpose A transpose, okay? And the main property of the matrices R is that R is an orthogonal matrix. Okay? So this is the main idea of having a vector. Here, the same thing. Gamma has to be an orthogonal matrix. Okay? And indeed, gamma is an orthogonal matrix. So this is what enables me to define X as a 4 vector in 4 dimensions. So X here, which is the coordinate, is going to be CT X, Y, Z. If I insist in putting C. Okay? So this is our 4 vector notation, and in special theory of relativity in general, I'm tending to collect 4 components together. One of them is temporal, and the other one is the spatial components. Okay? And always I have the fact that when I multiply X with X transpose, this has to give me an invariant quantity. Okay? Here it was invariant under rotation. Here it is invariant under Lorentz transformation. Okay? So this is the idea of having 4 vectors in 4 dimensions. This is why I can do this generalization. Just for some notations, I'm going to use what we call Einstein conventions. So I can write this matrix transformation as follows: X mu prime. So this is like a matrix indices. Gamma mu, lambda, mu, X mu, sum over mu. Okay? So this is the usual summation of indices in matrices. Okay? I'm going to drop this sum and keeping only the repeated indices. Okay? So when you see from now on a repeated index, this is what we call Einstein summation convention. Any repeated index means that we have a sum. Okay? Now, from the point of view of these 2 reference frames, sigma and sigma prime, every observer riding any one of them can actually measure the speed of light. And for sigma, the speed of light c is going to be the square root of x squared plus y squared plus z squared divided by the time. Okay? And the same thing also for, this is for sigma prime. It is the square root of x prime square plus y prime square plus z prime square over t prime. Okay? And you can see from that, I can construct a quantity which is basically zero, which is minus c squared t squared plus x squared plus y squared plus z squared is zero. Okay, and the same thing here also. Okay, and this quantity is zero in this case because it describes for me the propagation of light. But what if I have a massive particle, not actually light? In fact, in this case, okay, the velocity is going to be actually less than c, which means that this quantity is not going to be zero anymore. Is it going to be negative or positive? Negative. Okay? So for a negative, we are going to call this an interval. Okay? A space-time interval. Okay? Which is the difference between two events happening at different times and at different points in space as well. Okay? I'm going to generalize this, but this is what we call interval, and in this case it is negative. Okay? If the particle is going with a speed less than the speed of light. Okay? And if it's going with the speed of light, of course, this is going to be zero. And if the interval measure for me something outside, okay, the vicinity of the light cone, or if it's going with a speed more than the speed of light, okay, which of course is not possible, this is going to be positive. Okay? And in fact, I'm using these three categories to distinguish between physical and unphysical situations in special theory of relativity and in physics in general. So to talk about intervals more accurately, let us try to imagine that I have my light cone here. Okay? So this is time, this is x, this is y. Okay? And this is exactly 45 degrees. Okay, here I am setting again C to be 1. And the origin here is going to actually mark for me an event. Why it's an event? Because it happens at certain time, which is t equals 0, and it is happening also at certain position, which is x equal to 0 and y equal to 0. So this is a certain event here. Now I'm going to compare this event, let me call this event A, with another event here inside the light cone, which means the propagation or the evolution here from this point to this point cannot exceed the speed of light. It's always inside. Okay? So this is, let me call it B. Another point here, let me call it C, and a third point here, let me call it D. And let's actually try to see what the difference between these three intervals. This one, and this one, and this one. So, SAB, in a similar way as I define this interval, which is going to be minus C squared TB minus TA squared plus XB minus XA squared and so on. Okay? This interval difference, or this interval, sorry, is actually inside the code. So this has to be negative, right? because the particle going from this place to this place, or from this event to this event, is actually going with a speed less than the speed of light. Okay? Which means the slope here is always less than 1. Okay? Now for SAC, we can see that this is exactly the light propagation. Okay? Because the slope is exactly 1. And the last thing is SAD squared is going to be positive, which indeed I'm physical, because this sounds like a propagation with a speed more than the speed of light. Okay? So we call this space light, which is really not causal and not physical. And these two are the physical ones. Okay? One of them is representing light and the other one representing a particle, general particle with some mass. Okay? Any questions so far about special theory of relativity? This is just a very fast review to like the main idea and what we are going really to use maybe later on. Okay? Now, of course, special theory of relativity was just a theory for observers which are moving relative to each other with a constant speed. But of course, this is not life, because we know that objects can move relative to each other with some acceleration. But in order to include acceleration and forces in general, it's very important also to think about gravity. Why? Because gravity as a force, or the gravitational interaction according to Newton, was actually an instantaneous interaction. So if you take Newton's law of gravity and try to think of the sun disappeared, okay, at some moment, and you ask the question how long it takes the Earth to feel this, the answer in classical gravity is that it should feel it instantaneously, because nobody actually thought of the gravitational interaction will take some time, or it will have some velocity. These ideas came later on, okay? But for Newton and for the classical physicists, gravitational interaction and any type of interaction is actually mediated instantaneously. Of course, this is going to create a problem for because it's contradicting the concepts of special theory of relativity. And indeed, we need to formulate or reformulate gravity in such a way to go with the general principles of special relativity, which means that interaction should be constrained with a speed which is equal or less than the speed of light. So how can we do this theory? This is how Einstein thought, and it has a very, he started to have a very good idea when he started to think about the equivalence principle. Okay? How? First of all, let me review very quickly the idea of the equivalence principle and the idea of inertial mass and gravitational mass. So in fact, in mechanics, we have completely two different concepts. We deal with them as one concept, but they are not. They are logically separable or separated concepts. The concept of inertial mass, which is in Newton's second law. So this is the second law. It tells me that F is equal to MIA. And I'm putting a subscript here just to distinguish it as a mass from the other mass, which is coming from Newton's law of gravity, which I'm going to call it mg. Okay? So these two masses are completely different conceptual entities. The first one, basically, is the resistance of a motion of any object. The second one, you can think about it as a gravitational charge, something like Coulomb charge, but for gravity. Okay? So these two concepts are indeed different. This has something to do with motion, and this has something to do with the force itself, the nature of the force itself. Okay? But for some reason, we always have them identically the same. For all practical purposes, for all experimental verifications, so far, mi is equal to mg. Okay? But so what? What is the big deal? The big deal is the following. So, if we equate this, for example, in the case of gravitational force, okay, I'm going to have here mi A equals gmg m capital over r squared. So if these are equal, I'm going to actually cancel them, and you would have the fact that the gravitational acceleration for any object is going to be gm over r squared, meaning it will not depend on the mass of the object itself, right? So if m capital here is the mass of the sun, for example, okay, so let's have a caricature of that. So let's suppose that my sun is here, okay, and my earth is here, and I'm actually using this equation to calculate the trajectories, right? This is an acceleration. In order to get the trajectory, I need to integrate twice, right? Then I'll have two integration constants. And these two integration constants are going to fix for me the initial position and the initial velocity, right? So if I fix these two initial conditions, that's to say the initial position and the initial velocity, every trajectory for any object, whatever its physics content, is going to be the same, right? So if you have the Earth here with this initial condition and it is falling in the sun gravitational field, it's going to give you a trajectory. If you have an ant, okay, it's going to give you the same trajectory. If you have a human being, it's going to give you the same trajectory. Doesn't matter, because A here and the trajectory does not depend on any of these physical properties. So gravity is completely blind of the physics content of the object which is falling under gravity. Meaning that I can remove this whole thing that I'm calling a gravitational force and just think as if this sun is deforming the space or the environment around it in such a way that it creates this trajectory for everybody. Okay? And this is the main idea of general relativity. That gravitational force or the mass is deforming the space around it in such a way it creates trajectories for everybody to fall in. Okay? But somebody would ask, well, is this really unique to the gravitational force? For example, if we have Coulomb force, can I have it this way also? No way. This is unique for gravitational force. What I'm saying here is completely unique for gravitational force. Okay? So this is why I can describe gravitational force geometrically. Okay? As a geometry. Okay? And this is the main idea. So let's go one more step to confirm our idea by actually trying to formulate the equivalence principle, okay, with the elevator experiment. So in our experiment, let's suppose that we have two identical elevators and we have two twins, oh sorry, a twin. Okay, one of them is on Earth and the other one in space, and it is actually pulled with some acceleration which is equal to g. Okay, so the one on Earth, when he actually measures its weight on Earth, will give him some number. Okay, and what about this guy here? He's pulled by some rocket in space with the same acceleration. If he tries to weight himself here, is he going to get the same number? Yes, it's going to get the same number. But it's not only that. If this elevator is completely sealed, that he cannot see anything outside, there is no physical experiment this guy or this guy can do to distinguish between these two situations. There is no physical experiment which can make any of them distinguish, okay, if he is actually in a uniform gravitational field or if he is pulled by some constant acceleration rocket. Okay, this is what we call the equivalence principle. Okay, and it's very important because it has consequences. One of its consequences is, let's suppose that this guy was in some other planet which has like a very gigantic mass. Okay, and this guy is trying to do a laser experiment, okay, on Gigantica. Okay, and the same experiment, we are going to do it with the same elevator and the same man. Okay, where we have here a laser source, and this laser source is actually sending some light to the other side of the elevator. Okay, from an observer outside, this is going to do like this, right? And here, for this guy, okay, also if you see the source of laser here, it's going also to do the same bending here. And the reason why is that these two situations are identical, right? This bending here is basically because of the motion, right? You have seen the motion with acceleration, okay? So of course it's going to deform the trajectory for you because you are not an inertial observer. But here, since uniform gravity is exactly equivalent to a uniform acceleration, here also you have to see a bending of light. So this is what Einstein discovered in, I think, maybe 1911, okay? That the existence of a gravitational force has to bend light. And if I use light as a measuring device, metria, this light should map for me the space, okay? And if this mapping is going to get deformed or bent by this measuring device, it means that the space itself, okay, is deformed due to the existence of the gravitational field. Okay? So in order to describe gravity, I need to describe bending of space, or what we call in geometry curvature. Okay? And curvature, in order to describe it, you need tensors. Okay? So this is the first mathematical apparatus that you need. Tensor to describe curvature. Okay? But you need tensors as well for another reason. This other reason is that, as we said in special theory of relativity, special theory of relativity is a theory which actually says that all physical laws are invariant under change of inertial reference frames. But in general relativity, we don't have this condition. General theory of relativity describes for us physics. It has the same form in all reference frames, not in all inertial reference frames, in all reference frames. That's to say, we need a general coordinate transformation. If you are in some coordinate and somebody else is moving relative to you with some acceleration or even more complicated motion than just uniform acceleration, you can actually describe the two physics or two physical situations completely using general relativity, using tensors. Okay? So a tensor equation is an important equation to formulate this assumption or formulate this concept. Okay? So as I said, we need tensors for these two important issues in general relativity, for describing curvature and also for maintaining one of the principles of general relativity, which is physics or physics equation has the same form in all coordinate systems, okay, or in all reference frames. Okay, I'm going to interchange here these two words, reference frame and coordinate system. They are the same. Okay, good. So I hope this convinced you somehow that we need tensors. So let's actually go quickly on what is a tensor. So before we describe tensors as entities which have certain transformation laws, let's first describe what we mean by general transformation. Okay? So let's suppose that our space-time is described through certain coordinates, x, t, y, and z, for example. And let me call this x mu, okay? And in order to go to another reference frame or another coordinate system, I need to express the new coordinate in terms of the old ones. So t prime, for example, is going to be a function of t, x, y, and so on. X prime is going to be another function, t, x, y, and so on. Y prime, and so on. Okay? This is what we mean by a coordinate transformation. So in other words, when I take an x mu and transform it to x prime mu, this x prime mu is a function of x, where x here means the four components. Okay? And now we define tensors through its ranks. So first we have the zero rank tensor, which is a scalar. And a scalar actually is any function which obeys this transformation law. So it's formed in the new frame as a function of the new coordinate is always equal to phi of x. Okay? That's to say it has the same function, okay, in the new coordinate system. Okay? This is what we call scalar or invariant entity. Okay? So it is the same in all coordinate systems. The other rank is what we call a vector or a covariant vector. And the covariant vector is what we call the 1-0 rank. And it has a certain transformation law, which is A prime u is equal to partial x prime u by partial x nu A nu of x. Okay? Of course, A here is a function always of x prime. Okay? So this is how it transforms. Okay? Partial x prime u by partial x nu, and this is summed over A nu of x. Okay? But what about a general, and also I have a similar transformation law for, this is a contravariant tensor, contravariant vector, intercovariant. This is a covariant is the one with a lower index. Okay? And I can actually generalize this for any arbitrary number of ranks. So if I have t mu1 up to mu k, so this is upper indices, and lower indices is going to be mu1 up to mu k. This is partial x prime mu by partial x alpha 1, partial x, this is mu1 prime uk, partial x alpha k. Okay, partial x beta 1 by partial x prime mu 1, partial x beta, this is L, this is L, okay, x prime mu 1, this is L, partial x prime mu L, okay, and here I have t alpha 1 up to alpha k, beta 1 up to beta L. This is how it transforms. You can see that the upper indices are transformed with their x's, x prime upstairs, and the lower indices, their x primes of downstairs. Okay. So this is a general transformation law for any rank tensor. Okay. A tensor, of course, with rank k, comma l. Okay. So this is a rank k, comma l.
Shouldn't we put primes into the transform the tensor of the left?
I'm sorry?
Shouldn't we put
Yeah, sure. This is prime and it's a function of x prime. Yes, you are right. Otherwise it's confusing. T and T. Okay? So this is, of course, anything on the left always is T prime. Okay? Or always is prime, the new coordinate. Okay? Tensors, they have certain properties. I'm going just to skim over them very quickly. First of all, if you sum over two vectors like this, one is contravariant and the other one is covariant, you are going to get a quantity which is a scalar. So phi here is always transforming like a scalar. And the reason is the transformation law of the contravariant is going to cancel out the transformation law of the covariant, though it will remain, the whole thing will remain scalar. Okay? And also if you have another contraction like this one, for example, so if you are contracting two indices like this one, the one which is left is going to define the whole transformation of this entity. Let's call it Z, for example, and it's going to be a contravariant vector because we have a left index which is contracted. Okay? There is a very important identity here which is very useful in many ways. Sometimes we have tensors which are symmetric under the two indices. So if you interchange them, this is going to give you a minus sign. And we call this an antisymmetric tensor. Okay? Or a tensor which is antisymmetric in its indices. And sometimes we have a tensor which is symmetric, which means if you change this, this is a plus sign. Okay? And when you actually contract these two together, so S mu nu times A mu nu, this is always zero. When you contract a fully symmetric tensor with a fully antisymmetric tensor, it's always zero. Okay? It's very easy to actually prove this, so I would recommend that you try to prove it algebraically. Okay? Using just switching the indices. Okay? And you will end up with the same tensor, okay, with minus sign, which means something equal to its negative value, which means it is zero. Another important entity that we are going to deal with is actually metric. So what is the metric? So the metric is very important concept in general relativity. It is actually the main physical quantity through which we know everything about the gravitational system. So the metric is very similar to the concept of scalar potential, for example, in electrostatics. If I give you a scalar potential in electrostatics and I tell you what is the electric field and what other electrostatic properties, you can actually get out of this scalar potential, right? If you know the scalar potential, you know everything about the electrostatic system. It is the same thing with the metric here. The only difference is this is one function, this is 10 functions, okay? Because G mu nu is symmetric in its indices, okay? So, which means that you have 10 independent components, okay? you can count it. Think of it as a matrix, which is a symmetric matrix. It's a 4 by 4 matrix, right? Because the indices, everyone runs from 0 to 3. Okay? So it is like a 4 by 4 matrix, and it is matrix, and it is symmetric, which means it has 10 independent components. So as if we have 10 independent potentially that we are dealing with. We always can write down the interval or the interval difference that we talked about in special theory. We are going to generalize this concept into general relativity. So this is the infinitesimal difference between two events in the space-time. Okay? I can always write it in terms of the metric. Okay? And let's have some intuition about that. Of course, I can expand these components, okay? Like G00, dx node, dx node. X node here is time, okay? And x1 is x, x2 is y, x3 is z, if you like. 01, dx0, dx1, and so on. You do the whole expansion. Okay? As we said, repeated indices means summation. Don't forget that. Okay? So this is how we write the interval in terms of the metric, but the metric is a very important concept because it generalizes the distance, okay, that we know in 3 dimensions. So remember, for example, in Euclidean geometry, okay, if you have a general point here, okay, and you want to know the distance between these two adjacent points, okay, and you are having here the general coordinate system x, y, and z. Of course, you will do a projection. This is dy, this is dx, and this perpendicular is dz. And what is the relation between ds and these three guys? Anybody can tell me? ds squared. Just use Pythagoras theorem twice, right? So it is dx squared plus dy squared plus dz squared. Okay? So this is the interval for Euclidean 3-dimensional space with G11 is 1, G22 is 1, G33 is 1. Okay? It's trivial method. Okay? But another interesting metric is the metric on a sphere. For example, let me have a sphere here, and let me have a cap, and let us use spherical polar coordinates. Okay? So this angle is, let me call it theta 0, for example. Okay? And let's describe only a 2-dimensional surface of this sphere. Okay? This has a metric also, and this metric is simple. I can write it like this one. It is ds squared equals r squared d theta squared plus sine squared theta d phi squared. Okay? And for example, if I make this theta constant, and of course this is a 2-dimensional surface, so if I make theta constant and I let phi change, it's going to draw for me some curve. What is this curve? It's a circle, right? I'm fixing theta in spherical polar coordinate and moving the phi. So it's going to draw me a circle. In this case, in order to actually calculate the circumference of the circle, the length of the circle, I can use this interval, okay? Because theta is constant, any change in theta is 0. So this part I won't care about. So now ds is just r sine theta 0 d phi, right? Now if I want the whole circle from phi equals 0 to phi equals 2 pi, I need to integrate over this. So S is the integration here, which is going to give me R sine theta 0 times 2 pi, right? Indeed, this is correct. Why? Because this is the radius. If you project it, you will get this radius here, which is R sine theta, right? From just the right angle triangle here. This is R sine theta. And its circumference is just R sine theta 2 pi. Okay? Now, if you want to increase the theta and you make it on the equator here, your theta node is pi over 2. So sine pi over 2 is 1. And what you are going to get here is just R times 2 pi, the usual circumference of the circle. Okay? So you can see I can use this metric to do many things in geometry, and it is very important indeed. Okay? And the last thing I want to talk about here is, before I leave this, the metric, for example, as we are going to see, is related also to the Newtonian potential phi of the gravitational field. Of course, classically speaking, I can construct Poisson equation, right? For the gravitational field, right? Very similar to the electrostatic Poisson equation, okay? And phi here is the Newtonian potential. We call it the Newtonian potential. And it is related to G00 actually, in this way, that it is a constant plus some other constant times phi, okay? So as you can see, G00 is linear in phi, linear in the Newtonian potential, okay? So we are going to see that next time. But now, let's try to actually talk about derivatives and how can we do tensor derivatives, okay? The whole idea is the following. When you do a covariant, when you do a derivative for a tensor like a scalar quantity, so this is a scalar definition, so this is a scalar definition, and now let's actually take the derivative with respect to x prime. Because of this equality, I can replace phi prime with phi. Then I need to use the chain rule, because I need to take the derivative with respect to the dependence here, which is on x. Okay? So you can see here, I can think of this as a prime mu, and this as partial x mu by partial x prime, and this one as a mu. So you can see that taking a derivative for a scalar field is going to produce for me a first rank tensor, right? So it's not actually going to cause any problem. But actually this is about, this is only for the scalar. If I try to do that for a vector, for example, you can see that this is going to be complicated, because let's try that for a vector. So you can can see that I can take the derivative here with respect to b, and in this case, this part is going to transform like a vector. But I have another derivative which is going to complicate things, which is taking the derivative twice here. And this is going to complicate things, which means that the usual derivative of a first rank tensor or a vector is not in general a tensor, okay? Because of this complicated term. This doesn't transform like a tensor. This does, but this doesn't. So I need somehow to redefine my derivative in such a way to get rid of this part here, okay? And to do that, I need to redefine the derivative in this form. So I'm going to call the new derivative, which the covariant derivative, delta, and it's going to be like this. So I need to do the usual derivative plus some additional term defined by gamma. And this gamma is what we call connection, and it's related to the derivatives of the okay? Next time I'm going to actually discuss with you what is gamma and what is the meaning of gamma, okay? And how can we understand it geometrically. Okay, but keep in mind that for higher rank tensors, okay, I cannot use the usual derivative. I need to actually modify a bit my derivative, okay, to include an additional term which keep the tensor transformation of this whole thing. So now this whole thing is going to transform as a second rank tensor, okay? This one couldn't because of this extra term. Okay? Yes.
So script of partial x prime u, partial x alpha.
Which one?
Between the brackets. Yes. The solo script of the numerator, I think
That's wrong. Yeah. Yeah. There is some. This is new, yes. This is
u.
This is new. Yes, you are right. Yes, I have been fast. Thank you. Okay, so next time I'm going to talk about the meaning of this gamma, okay? Before we continue our discussion. Any questions so far? Any question about what we have discussed today? The basic concepts of special relativity and the basic concepts of general relativity. Any comment?
Very clear. Very clear. Yes.
Okay. Thank you. So we have a break now? So we have a break for 10 minutes or 15 minutes? What does the schedule say? 15 minutes? Okay. Zay.